Okay. Just checking on one last thing, and then I'm going to get started. There we go. Okay. There's a story about a boy in the 1800s. His name was Carl. And Carl was, he was like in either maybe late elementary school. I'm not really sure exactly what grade he was in, because elementary schools didn't exist the way they do back then. It was just like 50 kids in a room at desks with one teacher and junk like that. But he was young. And the teacher comes in one day and says to him, or says to the whole class, your assignment today is to add up all of the numbers, all of the whole numbers, from 1 to 100. And you have like an hour, let's say. Not really sure. It's an anecdotal story. The teacher mainly did not want to teach that day. The teacher just wanted to sit back and just relax and read a book and not have to worry about teaching children. So the students all took out their tablets, not an electronic tablet, but like a legitimate chalkboard tablet, and because that's what they used back then, and they went to work. Within a minute, Carl Goss walked up to the teacher, put his tablet on the desk, said, there it is. Teacher didn't really think anything of it, didn't even bother looking at it, told Carl to go sit down and put his head down. Over the course of an hour, all the students eventually turned in their work, turned in their chalkboard tablets, and class was over, and he sent them on their way. So, the teacher, after class, looked at the answers to this question, adding up all the numbers from 1 to 100. And they're all stacked. So he looked at the top one, wrong. Looked at the next one, wrong. Wrong approach, wrong work, scratch-outs, cross-outs, scribbles, everything under the sun that was just completely wrong with getting the answer to this question. No one was close. Everyone made a mistake at some point. Ran out of room. Like what have you. Because it's just like it's like a small tablet, like smaller than a piece of paper. And then he gets to the last one, which was Carl's because he put it down on the desk first. And Carl didn't have any work written whatsoever. The only thing he had written was the number 5,050, which is correct. The teacher, dumbfounded, eventually caught up with him the next day and asked, like, where did you get this answer from? You must have known the answer beforehand. You must have cheated. How did you get this answer? And Carl said, well, I thought about it in my mind and I got the answer. And it was correct. Carl Goss eventually grew up to be one of the greatest mathematicians of the 1800s. Probably the greatest mathematician of the 1800s, but that's an opinion. How did he get the answer? How did this young child, 8 or 9 years old, within a minute, get the answer to this question and not write anything down? This is the 1800s. He doesn't have any electronic devices. He can't search for anything. How did he do it? Carl, in his mind, and again, this is not what I'm teaching you today, but I just want to show you how he did it. In his mind, he horizontally took the numbers from 1 to 49. And then he took the numbers from 51 to 99, and he inverted them. And what I mean by that, he did this. And then what do you have when you add vertically? when you add vertically, you get 100s. How many pairs of 100 do you have? Well, you have 49 pairs of 100, which equal 4,900. What are the only two numbers in this original list that you did not use? Well, you didn't use the number 100, and you did not use the number 50. An 8-year-old figured that out in a minute. Of course, he grew up to be one of the greatest mathematicians of all time, greatest of the 1800s. Eventually, when he was an adult, he was able to figure out formulas and logic and rationale behind what he was doing and was able to prove it all on top of that. That is the point of today. Arithmetic and geometric sequences and series. What you have in front of you right here is actually what we call an arithmetic series. I'm going to define for you what a sequence and a series is. I'm going to define for you what arithmetic and geometric is along the way. Let's start with arithmetic. An arithmetic sequence is a list of numbers with a linear pattern. Now, something happens to be printing while I'm teaching. I hope you can all hear that. It says now, oh, there it goes. Now, what happens to be printing, I wonder? It's my son's work for today. If you'll excuse me for 30 seconds, I'm going to go deliver this piece of paper. Okay. And we're back. So an arithmetic sequence is a list of numbers with a linear pattern. And when I mean linear, I am talking a constant pattern. There is a common difference being added or subtracted to every single number within this list. And that is what is known as an arithmetic sequence. Now, I use the word sequence here. A sequence is just a list of numbers. Just a list of numbers with a pattern. That's all that it is. So, for example, 1, 2, 3, 4, ... There's an arithmetic sequence. Now, if you notice, the ... implies that it goes on forever. This is what is known as an infinite arithmetic sequence. It could also be a finite if I just did something like this. There, it stopped. Now it's a finite arithmetic sequence. So, infinite, finite, not really the point of this. I just wanted you to see what it looked like. Or you could have something like 3, 6, 9, 12, 15, ... There's an arithmetic sequence. Or 10, 4, -2, -8. There's an arithmetic sequence. Now that one's not as obvious. That one's subtracting 6 every single time. But it has to have a linear pattern. A linear meaning there is a common difference being added or subtracted to each term. A common, I'll just call it, I'll call it, I don't want to say difference just yet. Okay, I'll call it difference. I'll say something else afterwards. A common difference between consecutive terms. There we go. Meaning between 3 and 6, it added 3. Between 6 and 9, it added 3. Between 9 and 12, it added 3. Or between 10 and 4, consecutive terms, it subtracted 6. So like minus 6, minus 6, minus 6, or plus 1, plus 1, plus 1, or plus 3, plus 3, plus 3. They don't have to be whole numbers either. They could be fractional numbers if you wanted them to, but I'm not getting into the crazy, crazy details of what this thing is about. But that is an arithmetic sequence. Now, typically speaking, instead of having to list out all of these numbers, there was a way that was devised in which we could come up with a formula that was able to encapsulate what the sequence was going to say, and then we could just understand the formula. And the way that mathematicians decided to go about it for arithmetic sequences, this is specifically for arithmetic sequences. This is the arithmetic sequence formula. I don't even want to call it a formula, really. What do they call it here? Yeah, they just called for the nth term. I'll say for nth term. Something along the lines of this. A sub n equals a sub 1 plus parentheses n minus 1 times d. Now, the a sub n is representative of the nth term. It is very, very, very similar to f of x, f parentheses x, where a number could be inputted, and then there's an output. So, for example, if you wanted to find, let's say, the 10th term, you would plug a 10 in for n, and then, of course, a 10 would have to go in for this n as well. That would be the whole f of x thing. A sub 1, that little 1, represents the term that you're at, in this case, the first term. The d is that common difference that we just talked about before. This formula is going to come into play for everything that we're doing. So, for example, if I had the sequence 9, 16, 23, 30, and I needed, well, not that I needed, but let's just say I wanted you to find equation for the nth term. And then, using that formula, I want you to find the 50th term. Now, there's a reason why I just went crazy and said the 50th term. If I said, hey, what's the third term? Well, the third term is 23. Okay. What's the fifth term? Oh, well, let's just figure out what the common difference is. It's plus 7, plus 7, plus 7. So the fifth term should be 37. Yes. What's the 50th term? Oh, well, you'd have to add 7 until you get there. Or find the equation. And then once you have the equation, all you have to do is plug in a 50. So you could do something like this. A sub n equals a sub 1 plus parentheses n minus 1 times d. Knowing that formula is a good idea. It's just like a linear equation. It's like y equals mx plus b. It's a little different. The b is a little bit different, like a y-intercept type deal, but it's not what you think it is. I'm going to stick to this formula because it has a lot more applications than y equals mx plus b. So, I know what my first term is. It's 9. And I know what my common difference is. It's 7. So, a sub n equals 9 plus parentheses n minus 1 times 7. I'm going to have to simplify. Let me simplify by distributing that 7. And then let me simplify by combining like terms. So my actual formula is 7n plus 2. This answers that first question. Find the equation for the nth term. So again, if I wanted to find, let's say, again, the third term, which I know was 23, but if I wanted to find the third term, I'd plug a 3 in. 7 times 3 is 21, plus 2 is 23. Nailed it. Now you want to find the 50th term? You just plug a 50 in for the subscript. 7 times 50 plus 2. What is that? 352. So instead of counting up to the 50th term, you can easily just find the equation for the nth term and then use that equation to get the 50th term. Let's do another example. Let's say, I don't want to do that. Oh, that's a good one. That's a good one. Let's say that I wanted you to find the equation for nth term given a sub 5 equals 19 and d equals 6. Now, I don't give you the sequence. The only thing I've told you is that the common difference is 6, meaning it's plus 6, plus 6, plus 6 every time. And I've told you that the fifth term is 19. Now, I've already identified this as an arithmetic sequence. This section that we're working on is arithmetic, I should say, for the nth term of arithmetic sequence. Geometric uses a lot of the same terminology and notation, so I want to identify that as arithmetic. But if I wanted to find the equation for the nth term, I would need to use the information presented to me. The only piece of information that I don't have, that I need, is a sub 1. I need an a sub 1. Now, you could do one of two things. You could always, well, I'm at the fifth term. Why don't I just go backwards to the fourth, to the third, to the second, to the first? Yeah, of course. You could totally do that. You could absolutely do that if it's easy enough to count backwards. But what if I didn't give you the fifth term? What if I gave you the 500th term? If I gave you the 500th term, now you got to be counting backwards all that way. I don't want to do that. So, instead, I'm going to utilize the formula that I gave you at the beginning. Now, I know what the common difference is. I don't know what a sub 1 is. But I do know what a sub 5 is. A sub 5 is 19. A sub 5 equals a sub 1 plus parentheses 5 minus 1 times 6. I plugged a 5 in for n. I know what a sub 5 is. It's 19. Now, 4 times 6, 24. Now I can figure out what a sub 1 is. All I have to do is subtract those. A sub 1 should be negative 5. And it is. A sub 1 equals negative 5. Now I have all the information I need. See, back when you learned linear equations in Algebra 1, you were asked, okay, find the equation of the line. What do you need? Well, you need a slope, and you need a y-intercept. For arithmetic sequences, it's very similar. All you need is a common difference and the first term. That's what you need. A sub n equals negative 5 plus parentheses n minus 1 times 6. Now notice I went back to my original formula with the n. Now it's back to an n. Simplify. This is negative 5 plus 6n minus 6. So my a sub n should be 6n minus 11. You can always check it. The way you check it, well, number one, the slope should be 6, which it is. And two, if you plug that 5 in, you should get a 19. If you plug 5 in, 30 minus 11 is 19. It works. It absolutely works. Now, what if instead of something like this, instead of giving you the common difference and a term, instead I gave you the following. Example, let's say that I told you that the fourth term was 5. I'm going to keep it very simple here, actually. I'm going to keep it very simple here, I hope. The fourth term is 5. And the 12th term was 13. Again, I'm going to keep it very simple here. You could probably figure out what everything is just by these two terms by themselves. But I want to walk through what you could do in order to get this answer. Now keep in mind, the subscript is your input. What it equals to is your output. This is technically the ordered pair 4, 5. And this is technically the ordered pair 12, 13. And I want you to find the equation for nth term of arithmetic sequence. Now I'm telling you it's arithmetic. When you hear that word arithmetic sequence, or those words, I should say, arithmetic sequence, you want to think to yourself linear. It's a linear equation. Going back to the definition, an arithmetic sequence is a list of numbers with a linear pattern. And the d, the common difference, is your slope. So, d should then equal change of y over change of x. So it's 8 over 8, which equals 1. You could have figured that out by doing something else. By all means, you could have. But I'm doing it this way. What two things do you need to find the equation? Well, you need a slope and a y-intercept. No, wait, that's linear. You want a common difference and the first term, a sub 1. So, let's work backwards. A sub 4 equals a sub 1 plus parentheses 4 minus 1 times 1. This is that formula that I gave you at the beginning. A sub n equals a sub 1 plus n minus 1 times d. A sub 4, I know, is equal to 5. Was that for 3 times 1? So 3. So then a sub 1 should equal, was that 2? Yeah, 2. I don't know why I was writing that. A 2. Which, again, you could have found out by working backwards. A sub n equals the first term plus n minus 1 times 1, or simplifying that, a sub n equals n plus 1. I try to keep it very simple, for this example at least. If you have an arithmetic sequence, you can easily find these equations. Now, going to the Carl Gauss story. Carl Gauss, when he was older, eventually figured out an equation, a formula, for the sum of an arithmetic series. Now, to give you an idea, definition of series real quick. A series is a sequence being added up. That's all that a series is. It's a sequence that's being added up. Now, there's a couple things to go with that. There's certain notation that I could get into. In fact, that notation is probably going to pop up on various assessments. So let me introduce to you this. This is the capital letter sigma. Quote, sigma, it means the sum of. Now, what ends up happening with sigma, you could use any variable you want, but I'm just going to use n. Typically, n equals some kind of number. This is the starting term. There is some kind of a different number up here. This is the ending term. So for example, if it's n equals 1, you start at the first term. If it's n, or if the number appears like 50, then you end at the 50th term. I'll show you an example in a moment. And then there's some kind of an equation here. This is the equation for nth term, what we just did before. So for example, and I'll use one that we did before in a previous example. There we go, there's a good one. Let's say that I had 9 plus 16 plus 23 plus 30. This is one of our previous examples. And let's say it does not go on forever. Let's just say it stops right there at the 30. So it only goes to the fourth term. I would say, what's the sum of, and what was the formula that we used? 7n plus 2. 7n plus 2, starting with the first term and ending with the fourth term. That's what this sigma actually means. There is an equation afterwards. The equation is the formula for the nth term that you could find. The number at the bottom, n equals, again, it doesn't have to be n. It could be any variable. It could be k, it could be I, it could be j, it could be anything. I'm using n here. But n equals 1 means you start at the first term. And the 4 on top means you end at the fourth term. So that's what these four numbers added up equal this shorthand equation. To go to the Carl Gauss example, the Carl Gauss example was adding up all the numbers from 1 to 100, which I'm going to show you the formula for in a little bit. But he had 1 plus 2 plus 3 plus ... plus 100. His a sub n, if you actually were able to figure it out, the formula is just n. It's like 1n plus 0 or something like that. Technically, you don't have to have the 1, you don't have to have the plus 0, it's just a sub n equals n. Because then you plug in a 1, it's 1. You plug in a 2, it's 2. You plug in 100, it's 100. But his shorthand for this, something like this. The sum of the sequence n, starting when n equals 1 and finishing when n equals 100. That's what that would mean. So, just in case you see that shorthand a little bit later on with some of these examples. Again, we'll have practice with that. So what was Carl Gauss able to figure out? Carl Gauss was able to figure out the sum of an arithmetic series. The sum of an arithmetic series. And the way that he figured that out, well, I'm sorry, I'm not going to show you the way he figured it out. I'm going to show you what he figured out. But basically, the big S means the sum of, n is the number of terms that you're adding up. There it is. In order to figure it out, you just have to plug in n for the number of terms that you're adding. A sub 1 meaning the first term. a sub n meaning the last term, divided by 2. He figured this out when he was an adult, not when he was 8 years old. So the sum of the first 100 terms from 1 to 100 equals 100 times the first term plus the last term divided by 2. And if you did this, it should be 100 times 101 divided by 2, which, as we said before, 5,050. Now, I want to show you, on a slightly more detailed level, our previous example of 9 plus 16 plus 23 plus 30. Now, this is a simple example. You could do this example literally in 5 seconds or less. Boom, there it is. It's 78. That's what the answer should be. And it is. But we're only adding up 4 terms. What if we had to add up 50 terms? What if we had to add up 1,000 terms? That is where the formula comes into play. So, I'm adding up 4 terms. The first term plus the last term divided by 2. Now, according to the calculator, it should be 78. Again, a sub 1 plus a sub 4 in this case, because I'm plugging a 4 in for n, divided by 2 times the number of terms. 9 plus 30 divided by 2 times 4, 78. That's how this formula works. This is exactly how this formula works. It's a nice formula. It helps with a lot of what we're going to be doing here. So, let's try another example. One that we haven't seen before yet. Let's say the example I gave you was 12 plus 19 plus 26 plus ... plus 180. Now, clearly, this is arithmetic because it's plus 7 every time. I know what my first term is. It's 12. I do not know what my last term is. It's 180. In order to find the sum that I am looking for, I need to know what term 180 is. I need to know how many terms are being added up. So, let's see what we're going to do here. A sub n equals 12 plus parentheses n minus 1 times 7. I know that the first term is 12. I know that the common difference is 7. I don't know how many terms this is. This is a sub 1, this is a sub 2, this is a sub 3, this is a sub n. I don't know what it is. But I could do something like this. I'm going to simplify this a little bit. That's 7n minus 7. See, I don't know how many terms it took. I don't know what number was plugged in for n. But if I solve this, it will give me the n that gave me 180. So what happens? 12 minus 7 is what, 5? I'm going to subtract 5. Does that work? Yeah, I guess it does. 175 equals 7n, and then n equals 25. Nuts. I'm adding up the first 25 terms. That's what they're actually asking for. S sub 25 equals 25 parentheses first term plus last term divided by 2. Let's see, 12 plus 180 divided by 2 times 25. Nuts. 2,400. Right on the dot. Now, if I wanted to, I could totally do that here from 12 up to 180. I'm not going to do that by hand. Why would I bother doing that by hand? Instead, I'm going to rely on the formula because it's an arithmetic sequence, or series, I should say. There's a lot of other detailed problems that we can get into with this, which I am going to do with another video lesson. But for right now, I'm going to jump ahead to geometric. I'm going to come back and we're going to get a ton of practice. This is an intro to arithmetic and geometric. But I want to talk about geometric now. Let's talk about a geometric sequence. A geometric sequence is a list of numbers with, and for the lack of a better term, I'm going to say with an exponential pattern. A list of numbers with an exponential pattern. So, for example, I could start with any number I want. Start with 1. 1, 2, 4, 8, 16. There is a geometric sequence. It's a list of numbers with an exponential pattern, meaning there is some kind of a number being multiplied or divided every single time. Same number being multiplied or divided every single time. Another example could be something like 150, 25, 12.5, etc. You could say being divided by 2, or you could say multiply by 1/2 every single time. That is a geometric sequence, and it works. It absolutely works. Now I want to stay in the same style that I did before. There we go. Let's give a bullet point and say that there is a common ratio between consecutive terms. There is a common ratio between consecutive terms. Meaning if you took two consecutive terms and divided them, 25 divided by 50, you'd get a half. 50 divided by 100, you get a half. That's the common ratio. 16 divided by 8 is 2. 8 divided by 4 is 2. 4 divided by 2 is 2. Common ratio between consecutive terms. The geometric sequence formula, I'm going to have to get a new pen in a moment. For nth term, yeah, I'm going to get a new pen. Come on, you. Get me the pen I need. There we go. Yeah, the formula is this. A sub n equals a sub 1 times r to the n minus 1 power. Now, obviously, any assessment that I give you, these formulas would be readily available. It's just good to kind of know this one. First term, again, is a sub 1. R is that common ratio. It's a much simpler formula than it was before. It still has the n minus 1 in there, but instead of it being n minus 1 times d, it's r to the n minus 1 power. Okay. Let's see what we can do with it. Let's see. It's actually going to be a lot simpler to get the formula in these examples. Let's do this one. 1/2, 2, 8, 32, ... That is a geometric sequence. It's a list of numbers with a pattern. But it's a common ratio between each one. It has an exponential pattern. Exponential growth or decay doesn't matter. It's exponential. What's the common ratio? The common ratio is 4. Because you're multiplying by 4 every single time. 8 divided by 2, 32 divided by 8. What's the first term? Well, the first term is 1/2. Okay, it's weird. Just a sub n equals first term times 4 to the n minus 1 power? Yes. And that's it. A lot of people at this point might want to try and multiply the 1/2 and the 4, to which I would tell them no. Do not multiply the 1/2 and the 4. You're not allowed to at this point. You're not. You'd have to evaluate the 4 first. 4 to whatever power first, then multiply by 1/2 according to the order of operations. But that would be the formula. That's it. I don't know. Then let's say I wanted to find the 5th term. Let's say the 5th term. Now, I could figure out what the 5th term is just by kind of guessing here. Like, oh, it's just... No, I'm sorry, not even guessing. But 32 times 4, it should be 128. Yes, it should be 128. And it is 128. But let's just say I wanted to find the 5th term. 5th term, 1/2 times 4 to the 5 minus 1 power. That would be 4 to the 4th. Yeah. Times 1/2. 128. There's my 5th term. Yes. Geometric is a bit more straightforward than arithmetic. You just have to know how to use the formula. Let's try another one. Let's say... Oh, I don't like that one. I don't like that one either. Ooh, but I do like that one. Example. Find formula... I should say equation. Whatever. Formula for nth term of geometric sequence given a sub 4 equals 5 and r equals 6. Yeah, let's do that. Now, if I want to find the formula, all I need, and I'll write it up here, a sub n equals is the first term and the common ratio. That's all I need. I don't have the first term. I could work backwards to get that first term, or I could do something like this. A sub 4 equals first term times common ratio to the 4 minus 1 power, because it's n minus 1. And I plugged in a 4 for my n. Oh, but I know what a sub 4 is. A sub 4 is 5. So 5 equals a sub 1 times 6 to the 3rd power, 6 cubed, which is 216. A sub 1 equals this terrible fraction. Yes, it does. That's okay. Because a sub n equals my first term times my common ratio to the n minus 1 power. And you don't have to simplify because you shouldn't. You can't. You don't have to. You could leave it like that. You don't have to multiply those numbers together because you can't. You have to do 6 to the n minus 1 power first, then multiply by the fraction. There are various ways of simplifying this, but I'm not going to get into those details. But that's all. And then if you want to find like the 10th term, plug in a 10. Whatever you want to do. Now, let's talk about something a little bit weird. There is a formula for the sum of an arithmetic series. But the key is that that arithmetic series has to be finite. There is a finite formula for geometric, and there is an infinite formula for geometric. But I'm not going to get into the infinite today. I'm going to stick to the finite. But I say that because I have to specify that in my title. Formula for sum of finite geometric series. I'm emphasizing finite because there is a different formula for infinite, but I'm not getting into those details today. A series is just a sequence that's being added up. The sum would be something like this. It's a bit more complicated than what it was before. Let's just put it that way. A sub 1 parentheses 1 minus r to the n over 1 minus r. Now, going back to whatever you learned in algebra, you can't have a 0 in the denominator here, so r cannot be equal to 1. If it's equal to 1, then I'm sorry, you don't have anything that can be summed. It's just one, same number every single time. It's ridiculous. So, let's go back to one of our previous examples. Let's say that we had a half, 2, 8, 32. But I wanted to add those. All right, let's say I added them. Get rid of these little commas here. By the way, for the sake of argument, there we go. For the sake of argument, if you wanted to see it like that, it's the exact same notation, except it's a different formula. This is the formula for the nth term. But since this is geometric, I want to plug in the appropriate information. I know that a sub 1 is equal to a half. I know that r is equal to 4 because it's being multiplied by 4 every single time. And I know that I am adding up the first 4 terms. For the sake of argument, again, let's just see what it looks like. A half plus 2 plus 8 plus 32. I should be getting 42.5. I should be getting 42.5 if this formula is to be believed. Okay. The sum of the first 4 terms is a half times 1 minus 4 to the 4th divided by 1 minus 4. You notice I'm going to be getting some negative numbers here. That's okay. The negatives will cancel out. See what happens. I should be getting 42.5. 1 minus 4 to the 4th. Is that. Divided by, well, negative 3. Oh, this is weird. Huh. I get an 85. And the negatives canceled. Times 1/2. 42.5. It works out perfectly. It works out perfectly. These types of things. I love these things. Let's try one more. I want to try one more. I want to make sure that this works properly. Now, like I said, this is just an introduction. I am going to have a more complex example later on. Probably later this week or early next week. I haven't decided yet. But let's try this example. Let's say that you were told to figure out the sum to the following example. Now, this is a series because you're being asked to add up a sequence. That's what the sigma means, the sum of. This is geometric. It's geometric because, well, look at the formula. The formula is in the exact same form as the geometric formula for a sub 1 times r to the n minus 1 power, except instead of n, they're using k. But the weird thing is, they're starting at the third term and they're going to the 10th term. You're not adding up 10 terms. You're technically adding up 8 terms. You're technically adding up 8 terms. Because again, you're going from third to 10th, you're not counting the first or the second. You're not counting the first or the second term. You're only starting at the third term. So you're adding up 8 terms. Well, what's the first term that I should really plug in? Well, let's just say, since I'm starting at the third term, let me plug the 3 in. If I plug that 3 in, 3 minus 1 is 2, 2 squared is 4, 4 times 4 is 16. First term is 16. Okay. It's my common ratio. Well, my common ratio is in that formula, it's 2. That's all I need. That's all I need to figure this thing out. My first term is actually the third term in this series. It's the third term. But I need to plug it in as the first term. So I'm going to say, quote, first. Because it's really not the first term. It's really the third. All right. The sum of the first 8 equals my first term, 1 minus common ratio to the n power divided by 1 minus common ratio. Now, according to the answer key that I have, the answer should be 4,080. Let's see what he gets here. 1 minus 2 to the 8th divided by -1, because it's 1 minus 2, times 16. Nice. 4,080. Now, these examples get more extreme. They do. I'm thinking I'm going to have to do another practice video definitely before the end of this week. I think I might aim for Friday. I haven't decided yet. Of course, I'll keep you guys in the loop before I move forward with that. But I want to make sure that we get a lot of practice with this last unit that we are covering. Now, just to recap before I sign off, I have given you 4 main formulas for today. For an arithmetic, I have given you a sub n equals a sub 1 plus parentheses n minus 1 times d. And for the sum of an arithmetic, I have given you n parentheses a sub 1 plus a sub n over 2. For a geometric, I've given you a sub n equals a sub 1 times r to the n minus 1 power. And s sub n equals a sub 1 parentheses 1 minus r to the n over 1 minus r. These are not difficult formulas. They're not, as long as you have them in front of you and you don't have to memorize them. Personally, I do have them memorized, but that's because I'm a nut job. But again, this formula is for, or these top 2, I should say, for each successive arithmetic geometric. These 2 top formulas are finding the equation for the nth term. These bottom 2 formulas are finding the sum of the first n terms in whatever series that you're adding up. And like I said, there's a bit more that goes along with this. There is a bit more that goes along with this. Next time I go over an example, I'm going to get a little more practice with both of these. Perhaps I may get into the infinite, but I haven't decided quite yet. I might get into the infinite. We'll see. We shall see. Until next time, there should be some kind of practice that I'm going to put out in the next day or so. But like I said, the practice would be based on everything that we've done in this video. We'll see you guys next time.